Good morning, mathematicians. Welcome back to the office hour, to the office half hour, as I'm going to consider it. I'm going to put a timer on, actually. I know, but I must. It's a busy world. I got some shorts to record. Well, really, I've got some thesis to write, but I'm going to consider it. I'm going to put a timer on, actually. If I record my shorts, if I give myself more time, I can record some shorts, and schedule some of those to come out. Well, really, yeah. So I solved that CeeLo problem, actually. Maybe I'll wait till Ken's here to talk about it. But actually, that's one of the shorts I want to make. I want to put out a short today, which is the solution to the CeeLo problem. Good morning, Arad. Good morning. Yeah. So I don't know what else I want to talk about today. I did just see this post about a very obvious AI paper. But I mean, it's on Zenodo, so it wasn't going to be a good paper anyways. Yeah, I mean, disgusting. Incompressible Navier-Stokes. More like incomprehensible Navier-Stokes, am I right? But interesting. This is interesting, though. This is interesting. A likely nonsense paper, but they're not claiming to solve the Millennium Problem. That is interesting. That is a rarity. Establishing. Yeah. I mean, one thing it is interesting to you generally don't get why people do that. So you mean fully expecting it to happen, just don't get it. What, like total crackpottery? Publish crackpot papers? I don't know. I guess at some level they really believe it. Or AI papers, you mean? Yeah, this definitely looks very AI. We've got the numbering, we've got the bold. Yeah. Interesting. Okay. So they define their sigma admissible domains. So they seem to just swap one coordinate. And it's a domain fixed under swapping y coordinates. Okay. Yeah, but this is weird, right? Like you could just say omega equals this. Also, doesn't domain often refer to an open set? But then with periodic boundary conditions, what do you mean? What do you mean for a set to have periodic boundary conditions? It doesn't really make sense. I mean, a function on that set could be considered as a periodic function on the whole space of sorts. Not only papers, but AI stuff in general, and they play it off as something real. Yeah. I mean, that makes sense, right? We're all We're all looking for validation. We're all looking to be told we did a good job, and some people get desperate to hear that, I suppose, uh, and and so they turn to AI. I don't know. I don't know. I mean, it's also conceivable one could write a legitimate paper with the help of AI, with a very, very small amount of assistance in certain ways. I mean, the other day I used Claude to translate a paper into English. Well, therefore, and I needed those results for the preprint I'm working on. So yeah, there I used AI in a non-trivial way, right? And then the question is, so it's not too crazy to imagine it using it as a useful tool, and then still having it be your own work. But then where does that boundary lie? I mean, certainly, certainly probably not where this person's writing their things, but yeah. So I mean, yeah. In that case too, does that mean like I don't think I should say that I wrote my paper with AI in that case, right? And I'm sure you would agree as well. Um, but then where's the boundary, right? Where's that borderline? Okay, what if I just ask Claude how to format a table a certain way? I just copy that piece of the table in. And then does that count? At what point does it count? Translation is a more reasonable use case, yeah. Yeah. But then even, I don't know, like I could even imagine, would it count? Because, for example, it's very useful, to be in an office with a number of people. I go to the office. I discuss math with people. Even sometimes they might not understand the particular thing I'm talking about. Sometimes it's good to just talk out loud and rant to someone about something I'm stuck on. And just have a sounding board to bounce off of. Sometimes I even talk out loud when I'm alone in front of the board. And so it's conceivable that one could have use AI in that sense. A professional mathematician could use AI in that sense, and I suspect at this point in time, the AI is still not capable enough to say anything useful in response, right? But again, it's just sort of having something to just ping off of, right? But then, if I do that, did I use AI to help write the paper? I know this isn't exactly what we were talking about or what you were getting at with the ride, but it's a tangent I ended up going down. I think these are interesting questions to ask. Yeah, like at what point did I not write the paper? Yeah, I mean this is so very clearly AI though. Coming back to your real original point, this is so very clearly like copied and pasted. Yeah, but it's interesting. It's also like a matter of experience, right? It's like, um, I mean, yeah, this person. It's like I don't know why they're bothering doing what they're doing. This is just obviously insane. But like, um, if you right, I've talked about this before with the students that I caught, obviously using AI. It's like if you um if you don't know, if you don't understand mathematics that well, oh, they have an appendix. Interesting. Leray, they're Jean Leray, I guess. Is that does Navier-Stokes go back to Leray? Wait, really? Actually, I want to check out this paper. Was this a translated paper? Translated version? Nice. Anyways, I was gonna say, yeah, the sort of funny thing. Wait, this isn't translated. Huh? Oh, here we go. Hi, Gordon Freeman. My day is going well. I hope yours is going well as well. But yeah, it's this funny catch where it's like, if you know enough math to like successfully cheat using AI, then you probably don't need to cheat using AI. Although that's not exactly true, right? I'm thinking of this interview I saw where Magnus was talking about, what would he need to cheat? And for him, it's very little, right? So for an undergrad to totally cheat, they need a lot, and it's very obvious. And the thing is, they don't have the experience, so they look at a paper like this by Jean Leray and look at the output of ChatGPT, and they can't see the difference. Like, they physically can't see it because they just don't understand. They don't have enough experience with either things. But of course, as you get more experienced, you realize how obvious some of this is. But then it's interesting to me. Well, there's no cheating in math, right? The result is correct, or if it's not. But I'm thinking of this interview with Magnus Carlsen where he was talking about how if he did cheat, like basically no one would know, because at his level, right, he would just need one or two minor hints. Just so he said, what was it? He said something like, maybe just at 2 or 3 points in the game, I would just need something to tell me whether the position is winning or not. So not even like eval bar or best move or anything. And he was saying, like, probably if I just had that 2 or 3 hints, then I would just end up destroying everyone. And so it's interesting. I think the sort of thing is like that with I think it could end up going the way like that with AI slop, with people who don't really understand mathematics will just keep pumping out slop that's meaningless and obvious, and they themselves will be blind to seeing how obvious their slop is. And then the professionals who incorporate it in a meaningful way, you probably wouldn't even be able to tell, right? Wish I understood better mathematical physics to get what's so interesting about Navier-Stokes. Well, it's really hard. I think that's the main thing. I think it's really hard. There's probably more to it. I think the suspicion is if we solved Navier-Stokes, that would probably, aside from the problem itself, which, I mean, Navier-Stokes is about fluids. It's about how, like, gases and liquids move. So that's kind of a big deal. For the real world. But then also, I suspect that it's believed if we solve that those tools could be brought to bear on many differential equations. Would I recommend skipping Calc 2 for Calc 3? So the problem is this is impossible to answer because what Calc 1, Calc 2, and Calc 3 mean at different universities is totally different. So I have no idea where you're at. So I have no idea what Calc 1, Calc 2, or Calc 3 mean in this context. And it also depends, I don't know, like, do you need Calc 2 to take some certain course? Maybe it's a prerequisite for analysis 1. Um, also, also, um, yeah, what are your plans? What do you want to do? Are you in engineering, or are you in pure math, or are you in applied math or statistics? I mean, that all kind of makes a difference. Um, my guess is the content of Calc 2 and Calc 3 is such that you probably, if you're doing pure mathematics, that you probably don't need it. Um, but well, don't need it. I say that, but actually, you probably will need it in some way, depending on what field you go into. But calculus is everywhere, so probably it comes up in a non-trivial way at some point for you. But probably if you're in pure mathematics, like those courses are going to be more computational. You could probably just go ahead and skip that and learn it later. Multivariable calculus, yeah, okay. Um, yeah, again, I don't know. It's kind of tough. Right? Because my guess, if your course is calling it, if your university is calling it Calc 3, then my guess is that this is a very, hello, Naja. This is a very computational course, and probably in that sense. So if you are a pure math major, perhaps not the most important course, but I mean, multivariable calculus is also the foundation of like differential geometry. And that's kind of a huge field, and there's a lot of different areas of mathematics where you'll be encountering things like differential geometry, functional analysis, algebraic geometry. Even you could say that understanding multivariable calculus is useful for that, or if you're in statistics or machine learning or something like this. So I don't know. But then again, yeah, you're also saying, oh, you're in BC. Oh, British Columbia. Okay, you're close by. So you'll get to Calc 2, but you want to take Calc 2 and 3 concurrently. I mean, if you want to take them concurrently, then that's probably doable. I mean, if you have managed to teach yourself a bunch through self-study, and I don't know if your grades up until now. Calc BC. Oh, I see. Oh, I see. BC? I don't know what that is actually. You're in Calc. You're in Calc BC. I don't know what that means. But anywho, if your grades are good and you've been doing self-study and you've been looking at it, yeah, I mean, give it a shot. Why not? Why not go for it? Before counting? Calc before counting? I don't understand. Oh, it's American AP stuff. I see. So, like, advanced calculus. I see. Yeah, I mean, I say, why not go for it? Why not go for it? Even if it ends up being hard, try and do hard stuff. Respond whenever or never. Any quick tips on finding solutions for a system of polynomial equations? That's algebraic geometry, right? Yeah, I get that's yeah. You could sum up algebraic geometry as such. So yeah, there are no quick tips or solutions because famously difficult problem. Here's an extremely simple class of polynomials. Here's an extremely simple class of polynomials. And just the other day, I saw someone in a Discord server um, posted this like 50-page paper on like finding solutions in some case for like a very particular choice of A and B for some super particular case, and it used like modular forms and Galois representations and stuff. So that's an extremely simple equation. So yeah, there ain't any quick tips. Yeah, I mean, even for polynomials in 1 degree, right? Famously, there's no general formula in terms of for the roots in terms of radicals of the coefficients. So yeah, famously difficult problem. Yeah, my only quick tip would be learn as many techniques as possible for all the solvable cases. Computational algebraic geometry is a thing. Yeah, that's true. Yeah. If you're self-studying and interested in a specific thing, it's fine to skip it, but be prepared. You may need to trace back. Yes, this is true. This is true. Hi. Is the Krylov orbit method relevant to my research? Do I have any thoughts on the theory? You've been reading a bit about it. Very geometrically compelling. Yes, in fact, it is. In fact, I don't know the exact history of things, but I suspect that yeah, I could have the dates wrong. Maybe the order of influence goes in the wrong direction, but I suspect that David Vogel, who proposed and defined and proved a bunch of the things that are the background for my work, I suspect that he was inspired by the success of the orbit method. I'm not super familiar with the orbit method myself. I do have a book on it. I glance at it occasionally. I'd like to study it like more carefully and work through the examples. By the way, that's the first example that you look at in that book is the Heisenberg group, which has come up on stream just the other day. And yeah. So I would say yes. Does it directly apply to my work? No, not at the moment. But I would really like to better understand it, because I think yeah, there's a big influence there. Yeah. I mean, yeah. Yeah, like in very broad strokes, right? The orbit method says that you look at basically adjoint or you look at co-adjoint orbits. Say of some co-adjoint orbits of some Lie group acting on, I guess it's dual Lie algebra, and this should correspond to representations of G, and you can do things like geometric operations over here correspond to performing like algebraic operations like induction and stuff. And the idea is that you can also say maybe try and detect the unitarity of representations in terms of the geometry happening over here. And this is very much in line with like Vogel's perspective on the Piatek-Kasdan-Lustig hypothesis, right? Except the connection between co-adjoint orbits and representations is a little more direct in this case, because you're going from like orbits, you're going from like co-adjoint orbits of a complex Lie group two representations of that complex group. Things are more mysterious in the p-adic world, where we have orbits in a variety of Langlands parameters, and this is all like a complex variety, but then somehow we're connecting this to representations of a p-adic group. But again, it's very much the case that like operations here should correspond to operations over here, undoubtedly. And in fact, this has been proved in some cases that certain operations do correspond to certain operations. And I don't know about the detectability of unitarity or anything. But there is this whole theory of, as I've mentioned before, these Arthur packets that should have some geometric realization. And, well, what does that have to do? This has to do with somehow computing the vanishing cycles of some functor. And in particular, that has to do with looking at the co-normal bundles to orbits to some variety. And in fact, this is also very important in this theory. One looks at the co-normal bundles to orbits in this variety here. And there's things to say about that geometry. So I wish there was like a course on the orbit method or something at my uni. It'd just be nice. Sign up. It's just like, yes, I have a book. I could go and read about it, but there's other things distracting me. And if, when you sign up for a course, it just forces you to like learn something. What are some cool facts about the Heisenberg group? Yeah, so it seems like it's just separate triangular matrices, but it is. But one of the things is when you look at the Lie algebra, it encodes the basic the uncertainty principle can be viewed as a failure of the position operator and the momentum operator to commute, right? So I don't remember the exact constant we make it, but we end up making it some constant, right? Doesn't really matter what the constant is. We could scale things. And so, well, the momentum operator, we can view this as some sort of as like x, and we can view this as like a dx here. And anyways, if you take this as like a basic relation together with the fact that like the position operator should commute with itself, well, I guess that's always true. What's the other relation we want? But anyways, the point is, I'm fuzzy on the exact details, but if you basically set up some rules for the Heisenberg group, let's just bring up the Wikipedia. Yeah, basically, if you just set up some of the basic rules for the like commutation relations from physics, you end up getting the so here the name Heisenberg group comes from the canonical commutation relations. So I don't remember why the IH bar is supposed to be here, but okay, whatever. So basically you can encode the commutation relations in terms of these Lie algebra constants. The Heisenberg group then corresponds to it, and so in this way you can use it to like model some physical system. But then also it's really important, I really wish I had paid more attention. I sat in on this course that Stephen Kudla taught during the pandemic online, which was all about the Weil representation. And it touched on all of this stuff, but was more minded towards Langlands type things. And this is sort of, a very important thing. So the representation theory, tells you, the part of its like physical interpretation is how it acts on the L2 space of R n, or I guess R, just the real numbers for the sort of ordinary basic Heisenberg group. But then this relation here to symplectic vector spaces, so symplectic, you should always think physics. This is something to do, again, I'm out of my depth here, but this does have something to do with like Lagrangians and stuff, preserving some sort of symplectic form. And so, but this is also where the connection to, a well-known family of infinite dimensional unitary representations. This sort of is like the foundational part to defining the representation theory of the Weil representation, which is really important in like Langland's type stuff. Yeah, I wonder if we just go to the article in the Metaplectic group. What we'll see here. Yeah, modular forms, theta correspondence. Yeah, somehow is it just by way of the Stone-von Neumann theorem? Maybe it's just the fact that the Stone-von Neumann theorem applies to both. But I think if I understand correctly, I think it was Andre Weil who saw this in physics and was like, I'm just going to generalize this to an extreme level, and then did so. Like a really extreme level. Here we go. The automorphisms of the Heisenberg group fixing its center form the symplectic group. So the action of these automorphisms is equivalent to an action of the symplectic group. But only gives you a projective representation. Yeah. The Stone-von Neumann theorem, basically, it is it's a characterization of the representations. It's like if your representation satisfies this and this and this, then it's unique. If I recall correctly, let me see before I read the actual things. It's something to do with like, so a projective representation is just a representation that's only defined up to scalar multiple, so it's not necessarily a well-defined representation, and you want to know, but somehow, I don't know, I guess the theory is nicer, it's easier to work with or something, but you'd like to know if it comes from an honest-to-God representation, just by quotienting out the vector space. And I believe that is what it does for us. Any one of different formulations of the uniqueness of canonical commutation relations between position and momentum operators. Interesting. I've never heard it expressed so physically. I've seen it in like a very mathematical sense. Really? It's totally formulated physically like this. That's very interesting, because it's my understanding that there's a very the idea of Stone-von Neumann is that any two irreducible representations of the canonical commutation relations are unitarily equivalent. Okay. So I was a little bit wrong. Known as Weil relations. Okay. Oh, uniqueness of representation. Maybe this is here. One would like to classify separable Hilbert spaces up to unitary equivalents. One parameter unitary subgroups. Yeah, I need to go back and study this. I think Kudlow is planning on writing a book. I wonder if it's out. Kudla. Wow, I gotta go. It's been 34 minutes. Kudla Weil representation. The Krylov book, Lectures on the Method. Yes, fairly sprawling. Yes, I haven't found a book with more direct. Yes, so that's the book that I have as well and have been reading. Yeah, that's hey, look, my paper, my master's thesis. Don't read it. Oh my god. The content is fine. It's just the formatting was terrible. I had no eye for formatting at that point. I don't think this is his book though. Yeah. Notes on the theta correspondence. Oh, you had a question too? Well, you can just ask, Mr. L. I'm about to leave, but which the question may not be chopped liver. Well, feel free to ask. What does the Stone von Neumann theorem? Oh yeah, I talked about that one. Yeah. You just ask freely. Just ask freely. Oh, Bernstein-Zelevinsky classification. What am I looking at here? Huh. There's so much cool stuff to learn. Okay, maybe this is part of his book. I remember this stuff. Or is this actually a paper? I feel like I'd be so much better equipped to understand this thing now than like 5 years ago. Or 4 years ago, whenever it was. So much cool stuff, so many hours in the day. Anyways, back to this. Why is non-commutative geometry a thing? But non-commutative, but not non-commutative algebra. Non-commutative algebra absolutely is a thing. It absolutely is a thing. It absolutely is a thing. Yeah, 100%. I mean, non-commutative geometry is just roughly the attempt to make the wonderful geometric interpretation of commutative rings apply to non-commutative rings. So yeah, non-commutative algebra is in fact a necessary predecessor to non-commutative geometry wouldn't exist if non-commutative algebra didn't exist. Yeah. In fact, I have a book. I might get rid of it because there's so many books. It's very hard for me to ever get rid of a book because I have an addiction to collecting textbooks. But I've really never cracked this one open. I'm really trying to slim down. So it's on the fence right now. But it's a book called Non-Commutative Noetherian Rings. So yeah, I have an old and popular textbook because I've seen it everywhere. That's committed to the Noetherian case of non-commutative rings. That's non-commutative algebra for you. Okay, well, time to go prove some things for me and for you. It's a good day to push oneself to try and hit a faster 5K time as well. Get those brain